We pick up right where we left off from the previous video, and we're going to introduce a notion of what are called primitive roots. So what we saw in the last video was, for any positive integer n where a is relatively prime to it, the order mod n of a must be a factor of phi of n. Also, the powers of a will produce exactly that many different values mod n, whatever the order was. All of those powers will be relatively prime to n. We also know that if we can find phi of n different things mod n, all relatively prime to n, that will be a reduced residue system mod n. So the powers of a will actually form a reduced residue system mod n if and only if the order of a is exactly phi of n. The order of a must be a factor of phi of n, so phi of n is the biggest the order could possibly be. That's exactly how many different values mod n will get if we list out all the powers. But if I can get this many phi of n different values mod n, then I will have a reduced residue system mod n. So if I can list out this many distinct values mod n, and this is all of the values I can find, I will make a reduced residue system mod n. Therefore, we define a to be a primitive root modulo n if the order mod n of a is the biggest it could have been, phi of n. In other words, if the powers of a will form a reduced residue system mod n. So if a is a primitive root modulo n, the multiplicative structure of a reduced residue system, remember we have things that are relatively prime to n, that has to do with multiplication, and the product of any two such things will again be relatively prime to n, can actually be replaced with an additive structure on the exponents, since all elements of the reduced residue system are now actually replaceable with powers of a. When I multiply two powers of a, what I really get to do is simply add the exponents. So for example, we saw in the previous video, 3 is a primitive root mod 7. So instead of writing 1, 2, 3, 4, 5, 6 as the standard reduced residue system, we can write 3 to the first through 3 to the sixth. Most people would generally replace 3 to the sixth with 3 to the 0. 3 to the sixth is 3 to the order, which is equivalent to 1, and generally we would write that as 3 to the 0 is equivalent to 1. So usually instead of listing out the powers 1 through the order, we would start with 0 and go to 1 less than the order. So therefore, this set is a reduced residue system modulo 7. In the standard reduced residue system mod 7, multiplication might not be immediately obvious. Okay, 3 times 6 is 18, but which element of the reduced residue system is that equivalent to? It's not very difficult to see that 18 is equivalent to 4 modulo 7. But easier would be something like 3 cubed times 3 to the 4th is equivalent to 3 to the 7th, and 6 was the order, so I can take that out and just say 3 to the 7th is equivalent to 3 to the 1st, mod 7. Therefore, 3 cubed times 3 to the 4th is equivalent to 3 to the 1st, mod 7. It replaces the question of doing multiplication with doing addition within the reduced residue system mod n. However, is it true that there are always primitive roots to find? If n is a positive integer, are there primitive roots? Are there special numbers whose powers form a reduced residue system mod n? If so, how would we find them? Not every number n has a primitive root. So for example, let's show there isn't a primitive root mod 8. All we need to do is show that no element of a reduced residue system mod 8 is a primitive root. So instead of the standard reduced residue system 1, 3, 5, 7, I'm going to replace 5 with negative 3. They are equivalent mod 8, and I'm replacing 7 with negative 1. Phi of 8 is 4. So in order to show that there are no primitive roots mod 8, we just need to show that no element has order 4. Now the order of 1 is always 1, and the order of negative 1 is 2 as long as the base is 3 or larger. So definitely those two things are not primitive roots. But 3 or negative 3 squared would be equivalent to 1 modulo 8. So the order of either 3 or negative 3 is 2. So nothing had order 4. Therefore, there are no primitive roots modulo 8. So do primitive roots always exist? No. There are certain bases for which there are no primitive roots. 8 is one of them. we're actually going to spend a few lessons completely answering the question of which bases do have primitive roots and which don't. Before we start that process, however, here's a useful result. Let n be a positive integer, a be relatively prime to it, then for any k, which is an integer, the order of a to the k can be computed out of the order of a divided by the GCD of the order and this exponent k. So for convenience, to prove this, I'm going to call the order mod n of a, I'm just going to call that m. So a to the m is equivalent to 1 mod n because there's the order. Also for convenience, this greatest common factor of the order of a and k is going to be called d. So d must be a factor of the order of a, which we've already denoted as m. So m can be written as d times something. So the statement of the theorem now becomes the order mod n of a to the k is this order, which we called m, divided by this GCD, which we called d, and notice here, that's going to be just j. We can also write that k, since it's also divisible by this GCD, k is written as the GCD times I. Then this j and this I must be relatively prime to one another, because out of m and k we factored out the GCD already. So a to the k raised to the j power. I just do some shenanigans with the exponent. That's a to the kj. I replace k with di. I then call that a to the dj to the I power, and dj was m. In other words, a to the k to the j is the same as a to the m to the I. A to the m, however, was equivalent to 1, so a to the k raised to the j power must also be equivalent to 1 mod n. Therefore, whatever the order of this number is must be a factor of this exponent. This number a to the k, we found a positive power of it equivalent to 1 mod n. Therefore, that power must be a multiple of whatever the order was. We want to show these two things are equal, and we've at least shown that the order of a to the k is a factor of j. If we can show that j is also a factor of the order, then they must be equal, and that will be exactly what we wanted to show. So let's finish that proof. N is a positive integer, a is relatively prime to it, k is any integer. We said, just for notational convenience, the order of a is going to be written as m. The GCD of the order of a and this integer k is going to be written as d. Then we wrote m is equal to dj, k is equal to di, where I and j are relatively prime. Our goal was to show that the order of a to the k is equal to j, and what we have shown is that the order of a to the k is a factor of j. So now consider that a to the k raised to its own order is definitely going to be equivalent to 1 mod n. It's just what the order is. A number to that power should be equivalent to 1 mod n. Properties of exponents let me claim this is a to the k times the order of a to the k. But now what I have is a raised to some power is equivalent to 1. Therefore, the order of a, which we called m, must be a factor of that power. So m times something is that power. M was already written to be as dj and k was di, and now I can cancel d from both sides. So j times t is simply equal to I times the order mod n of a to the k. Now our goal, remember, was to show these two things are equal. We've shown that this order is a factor of j. Can I somehow claim that j is a factor of this order? Well, j is definitely a factor of I times the order. But j and I were relatively prime. So if j is a factor of I times the order and it's relatively prime to I, it must be a factor of the order. So j is a factor of the order of a to the k, but the order of a to the k was also a factor of j. Therefore, they are equal to each other. In other words, the order mod n of a to the k is equal to the order mod n of a divided by the greatest common divisor of the order of a and the exponent that we raised a to. Let's see an example of how this is useful. Given that the order mod 21 of 2 is 6, what's the order mod 21 of 16? 16 is 2 to the fourth, so we can simply apply that formula. The order mod 21 of 2 to the fourth can be computed as the order mod 21 of 2 divided by the GCD of that order and the exponent 4. And we were given that the order mod 21 of 2 is 6. So I replace that as 6 over the GCD of 6 and 4, 6 over 2, aka 3. Therefore, the order mod 21 of 16 would be 3, assuming that the order mod 21 of 2 is actually equal to 6, which it is. And that's a lot easier than trying to compute powers of 16 and reducing them mod 21. We can derive two corollaries from that result. If A is not a primitive root modulo n, then no power of A is a primitive root modulo n. Well, if A is not a primitive root mod n, its order is less than phi of n. Remember, it has to be a factor of phi of n, and if they were equal, it would be a primitive root. So it's a factor of phi of n, but it's not phi of n, it must be smaller. Then for any power a to the k, the order mod n of a to the k can be computed through this formula here. The denominator is the GCD of two numbers, so the denominator is at least 1. Therefore, this quotient can't be any bigger than the order mod n of a. We have the order mod n of a divided by something. But the order mod n of a was smaller than phi of n. So altogether, the order mod n of a to the k is also smaller than phi of n, so it's not a primitive root either. So if you find a number that isn't a primitive root, all of its powers are also not primitive roots. Another corollary we can derive, if a is a primitive root mod n, then if I raise that number to a power, this new number a to the k is also a primitive root mod n if and only if the exponent k is relatively prime to phi of n. So we just have to compute what's the order of a to the k. Well, we apply the formula that we just derived. Since a was assumed to be a primitive root, this order is phi of n, which I replace in both locations. Now, is a to the k also a primitive root? Only if this order is phi of n. In other words, if this quotient is phi of n. This quotient is phi of n if and only if the denominator is 1. In other words, the exponent k was relatively prime to phi of n. So that's another handy little corollary that we will see pop up again later.